At the turn of the 20th century, physics appeared complete. The laws formulated by Newton and refined over centuries had described motion, gravity, heat, light, and mechanics with extraordinary success. Engineers built bridges, astronomers predicted eclipses, and machines transformed societies, all using the same classical principles. To many, it seemed that nature had revealed all its essential secrets. The universe looked like a vast, perfectly ordered machine, governed by precise laws that allowed the future to be predicted if the present were known. Yet beneath this confidence, cracks were already forming, quiet at first, then impossible to ignore. The first signs of trouble emerged from experiments that refused to obey classical expectations. When physicists studied the radiation emitted by hot objects, they encountered a problem so severe it was later called a catastrophe. Classical theory predicted that as the wavelength of light became shorter, the energy emitted should increase without limit. In reality, this did not happen. Objects glowed, but not infinitely. Measurements stubbornly contradicted theory. This was not a small error that could be corrected with a tweak or an extra assumption. It was a fundamental failure. The equations that worked beautifully for everyday phenomena collapsed when applied to atomic scales. At the same time, investigations into the structure of matter revealed even deeper inconsistencies. Atoms, once imagined as tiny solid spheres, turned out to be complex systems with internal motion. According to classical electromagnetism, an electron orbiting a nucleus should continuously lose energy and spiral inward until the atom collapsed. But atoms were stable, matter existed, the world did not disintegrate. Once again, theory and reality stood in direct conflict, and no amount of mathematical adjustment could resolve the contradiction. Light itself became a source of confusion. For much of the 19th century, it was understood as a wave, a conclusion supported by experiments showing interference and diffraction. But then came observations that demanded a particle-like explanation. Photoelectric effect showed that light could knock electrons out of metal surfaces only if it carried enough energy, regardless of its intensity. Classical wave theory could not explain why brighter light sometimes failed while dim light of a higher frequency succeeded instantly. The behavior of light refused to choose a single identity. These problems were not isolated. They accumulated, each one eroding confidence in the old framework. Physicists tried to patch classical theory, introducing ad hoc assumptions, hidden mechanisms, and temporary fixes. But the more they patched, the more fragile the structure became. It was like repairing cracks in a dam while the water pressure continued to rise. The failures were not due to poor measurements or incomplete data. They were precise, repeatable, and undeniable. This growing crisis forced scientists to confront an uncomfortable possibility. The foundations of classical physics were incomplete. The assumptions that space and time were continuous, that particles had well-defined positions and velocities at all times, and that causes led to predictable effects no longer held at the smallest scales. The universe behaved differently when examined closely, and the old language of certainty could not describe what was being observed. The psychological impact of this realization was profound. For generations, physics had represented the pinnacle of rational certainty. It was the discipline that offered clear answers, firm predictions, and universal laws. Now it faced questions it could not answer using its own tools. Younger physicists sensed opportunity, while older ones often felt unease. Some resisted the implications, hoping that a hidden classical explanation would eventually restore order. Others recognized that a radical shift was unavoidable. Into this environment stepped a new way of thinking, one that did not begin by preserving classical intuitions, but by listening carefully to what experiments revealed. Early quantum ideas emerged cautiously, often proposed as temporary mathematical tricks rather than statements about reality. Energy appeared in discrete packets. Atomic systems behaved as if only certain states were allowed. These ideas worked, but they raised a more troubling question. What did they mean? The crisis was no longer merely technical. It became philosophical. If nature could not be described in continuous terms, what replaced them? If particles did not follow precise trajectories, what did it mean to say that something existed at a particular place? If prediction could only be statistical, was science abandoning its commitment to causality? These questions haunted the development of early quantum theory, and they demanded thinkers who were willing to rethink not just equations, but the meaning of explanation itself. This was the world in which Max Born worked. He did not inherit a stable discipline. He entered a field in turmoil. The uncertainty and confusion were not obstacles, but signals that something fundamental was changing. Born understood that the crisis of classical physics was not a failure of science, but a sign of its growth. When old concepts break, it is because reality has outgrown them. What distinguished this moment from earlier scientific revolutions was the depth of the challenge. Classical physics had not simply made inaccurate predictions. It had shaped the very way scientists imagined reality. To move beyond it required intellectual humility and conceptual courage. The crisis demanded acceptance that nature does not conform to human expectations of simplicity or certainty. As experimental evidence mounted, it became clear that no return to classical certainty was possible. The universe at small scales was governed by rules that did not align with everyday intuition. The task was no longer to rescue the old world, but to build a new one capable of explaining what was actually observed. This transition marked one of the most dramatic turning points in the history of science. The collapse of classical physics did not end knowledge, it redefined it. It forced physicists to recognize that understanding does not always mean seeing clearly, and prediction does not always mean certainty. Out of this crisis emerged a new framework that would transform technology, philosophy, and humanity's image of the universe. But before that transformation could occur, someone had to accept that the old foundations were gone and that probability, not certainty, might be the deepest truth nature was willing to offer. When Erwin Schrödinger introduced his wave equation in the mid-1920s, it was immediately recognized as one of the most powerful tools ever created in physics. The equation worked. It predicted the allowed energy levels of atoms with stunning accuracy and explained patterns in atomic spectra that had baffled scientists for decades. Yet despite its mathematical success, it raised a profound question that no one could avoid for long. What exactly was waving? The equation described a smooth, continuous wave spread out over space, but experiments revealed particles arriving as localized, discrete impacts. The mathematics was flawless, but its meaning was deeply unclear. Many physicists initially assumed that the wave described a real physical entity, something like a ripple in an invisible medium. This idea was tempting because it preserved a sense of continuity and determinism. If the wave were real, then the particle might simply be a concentrated part of it, guided along a well-defined path. This interpretation offered comfort because it seemed to rescue classical intuitions from total collapse. But the more carefully the theory was examined, the more problems this view created. The wave extended everywhere, even to regions where the particle was never detected. If the wave were physically real, it implied that something existed in places where nothing was ever observed. It was at this critical moment that Max Born made his decisive contribution. Rather than forcing the mathematics to fit an intuitive picture, he reversed the approach. He asked what the equation actually predicted, about measurable outcomes. What experiments recorded were not waves filling space, but individual events: a dot on a photographic plate, a click in a detector, a flash of light. Each event was localized and discrete. Born realized that the wave did not describe the particle itself, but the likelihood of these events occurring at different locations. This insight led to a radical reinterpretation of the wave function. Its squared magnitude, Born proposed, represented a probability distribution. The wave did not tell us where a particle was. It told us where it could be found, and with what likelihood. Before measurement, the particle did not possess a definite position in the classical sense. The theory did not hide missing information. Instead, it provided the most complete description possible, a map of probabilities. The consequences of this idea were revolutionary. For the first time in the history of physics, uncertainty was not a limitation of measurement or knowledge, but a fundamental feature of nature. Even with perfect equations and complete information, the outcome of a single event could not be predicted with certainty. Only statistical patterns over many events could be calculated. This was not ignorance, it was structure. The universe itself, at its deepest level, spoke in probabilities. Born's interpretation immediately clarified the strange duality of waves and particles. The wave function evolved smoothly and deterministically according to Schrödinger's equation, but measurement produced discrete outcomes. The probability interpretation explained how both aspects could coexist without contradiction. The wave governed the evolution of possibilities, while the act of measurement selected one outcome from among them. There was no need to imagine hidden trajectories or unseen mechanisms guiding particles behind the scenes. The theory was complete as it stood. This idea also resolved long-standing puzzles in scattering experiments, where particles deflected off targets in unpredictable ways. Classical mechanics would require precise initial conditions to explain each individual deflection. Born's probabilistic view showed that only the distribution of outcomes mattered. The wave function could be used to calculate the probability of scattering in different directions, and experiments confirmed these predictions with remarkable precision. Once again, probability proved not only philosophically radical, but empirically correct. Resistance to this interpretation was immediate and intense. Many physicists struggled to accept that nature did not determine individual outcomes. Albert Einstein famously objected, insisting that a deeper, hidden level of reality must exist beneath the probabilities. To him, randomness was a sign of incompleteness, not truth. Born respected Einstein deeply, but he did not retreat. He trusted the mathematics and the experiments. Again and again, attempts to restore determinism failed, while the probabilistic framework continued to succeed. What made Born's contribution especially powerful was its humility. He did not claim to know what reality really is behind the equations. He focused on what the theory could say about observations. This restraint gave quantum mechanics a clarity that allowed it to grow rapidly. Physicists could calculate, predict, and build without becoming trapped in endless metaphysical debate. The probability interpretation provided a stable foundation on which the rest of quantum theory could be constructed. Over time, this view reshaped the scientific understanding of causality. Causes no longer produced single effects, but ranges of possible outcomes with well-defined probabilities. Laws of nature became statistical laws, precise in their predictions of patterns, even while remaining silent about individual events. This shift did not weaken science, it strengthened it. Quantum mechanics became the most accurate theory ever developed, matching experiments to extraordinary levels of precision. The practical implications were immense. Technologies that define modern civilization depend on the probabilistic behavior of quantum systems. Semiconductors, lasers, medical imaging, and quantum information science all rely on calculations rooted in Born's interpretation. Every time a device operates according to quantum principles, it quietly confirms that probability waves describe reality better than certainty ever could. Max Born later reflected on the philosophical weight of his idea, acknowledging that it required abandoning deeply held intuitions about the world. But he never regretted the shift. He understood that science advances not by preserving comfort, but by accepting truth, however unsettling. His interpretation did not destroy realism, it redefined it. Reality was no longer a collection of predetermined facts, but a structured landscape of possibilities. In accepting probability as fundamental, Born did more than solve a technical problem. He changed the meaning of explanation in physics. He showed that understanding does not always mean predicting exact outcomes, and that the deepest laws of nature may describe tendencies rather than certainties. This insight, born from careful attention to mathematics and experiment, remains one of the most profound contributions ever made to human knowledge. For centuries, science was built on a simple and powerful assumption: the universe is deterministic. If the position and motion of every object were known at a given moment, the future could, in principle, be calculated with absolute precision. This idea was not merely a scientific principle, it was a worldview. It shaped how humanity understood cause and effect, responsibility, predictability, and even free will. Nature in this picture was a vast clockwork mechanism, and physics was the art of reading its gears. The rise of quantum mechanics, and particularly the probabilistic interpretation introduced by Max Born, shattered this vision in a way that no previous scientific revolution had. Determinism had survived many challenges. Even chaotic systems where small changes led to large effects were still deterministic in principle. The unpredictability arose from practical limitations, not from the laws themselves. Classical physics never suggested that outcomes were fundamentally undetermined. It assumed that randomness was a reflection of ignorance, not an intrinsic feature of reality. This belief was deeply embedded in scientific thinking by the time quantum phenomena forced their way into attention. At the atomic scale, however, experiments produced results that refused to align with deterministic expectations. Identical particles, prepared under seemingly identical conditions, produced different outcomes. Electrons passed through barriers they should not cross, and their paths could not be tracked without destroying the very patterns scientists sought to observe. The behavior was not merely complex, it was irreducibly unpredictable. No refinement of measurement techniques eliminated this uncertainty. The randomness persisted no matter how carefully experiments were designed. The probability interpretation of quantum mechanics confronted this fact directly. It did not attempt to explain randomness away. Instead, it accepted that nature does not assign definite outcomes to individual events until they occur. Before measurement, a system is not in a single, well-defined state in the classical sense. It exists as a set of possibilities, each with a calculable probability. The laws of physics govern these probabilities with extraordinary precision, but they do not dictate which possibility will be realized in a given instance. This shift marked a profound break from determinism. It meant that even perfect knowledge of a system's wave function does not allow the prediction of a single outcome with certainty. The future is constrained, structured, and statistically predictable, but it is not fixed. Nature does not follow a script in which every event is prewritten. Instead, it unfolds within boundaries defined by probability. This idea provoked intense philosophical resistance. Many scientists found it difficult to accept that the universe itself could be indeterminate. They sought hidden variables, unseen parameters that would restore determinism beneath the surface of quantum behavior. According to this view, probability was merely a reflection of incomplete knowledge, not a fundamental principle. If only the hidden details could be uncovered, certainty would return. Decades of theoretical and experimental work tested this hope. The results were decisive. Experiments based on mathematical inequalities showed that no local hidden variable theory could reproduce the predictions of quantum mechanics. Nature itself violated the constraints that determinism would impose. These findings did not merely support probability as a useful tool. They demonstrated that indeterminacy is woven into the fabric of reality. The abandonment of determinism did not lead to chaos or intellectual surrender. On the contrary, it gave rise to a new and remarkably powerful form of scientific understanding. While individual events could not be predicted, the collective behavior of large numbers of events followed precise statistical laws. The uncertainty of single outcomes did not undermine reliability, it enhanced it. Predictions became probabilistic, but they were also extraordinarily accurate when tested against experiment. This new framework transformed the concept of causality. Causes no longer guaranteed effects, they influenced probabilities. An action does not determine exactly what will happen, but it shapes the range of possible outcomes and their likelihoods. This probabilistic causality proved sufficient to explain everything from atomic stability to chemical reactions and nuclear processes. It provided a coherent and predictive structure without relying on certainty. The implications extended far beyond physics. Philosophers revisited long-standing debates about free will and necessity. If the universe is not fully deterministic, then the future is not entirely locked in by the past. While quantum indeterminacy does not automatically grant human freedom, it undermines the idea that all events are rigidly predetermined. Reality at its deepest level allows for genuine openness. Even our understanding of knowledge itself had to change. Classical science aimed to describe how things are at all times independent of observation. Quantum mechanics revealed that observation plays an unavoidable role in defining outcomes. The act of measurement is not a passive recording of pre-existing facts. It is an interaction that helps bring one possibility into reality. This does not mean that reality is subjective, but it does mean that it is relational. What can be said about a system depends on how it is observed. Despite its radical nature, the probabilistic view proved to be extraordinarily fertile. It enabled the development of technologies that depend precisely on quantum uncertainty. Tunneling effects, probabilistic transitions, and discrete energy levels are not flaws to be corrected. They are resources to be harnessed. Entire industries now rely on phenomena that would be impossible in a deterministic universe. Max Born understood that accepting indeterminacy required intellectual courage. It meant relinquishing the comfort of absolute predictability and embracing a universe that is fundamentally subtle. Yet he also recognized that this shift did not diminish science. It refined it. Science became less about foretelling exact futures and more about mapping the structure of possibilities. In this new vision, order and uncertainty coexist. The universe is not random in the sense of being lawless. It is governed by strict mathematical principles that define what can and cannot happen. But within those constraints, outcomes are not fixed until they occur. This balance between structure and openness is one of the most profound insights of modern physics. The transition from determinism to probability represents one of the deepest changes in human thought. It altered how we understand nature, causality, and knowledge itself. By accepting that uncertainty is not a weakness but a fundamental feature of reality, quantum mechanics revealed a universe that is richer, more flexible, and more surprising than the clockwork cosmos of classical physics ever allowed. At the heart of quantum mechanics lies a rare and powerful alliance between abstract mathematics and physical reality. Unlike classical physics, where equations often describe familiar motions and forces, quantum theory emerged from mathematical structures that seemed detached from everyday experience. Complex numbers, operators, and multidimensional spaces became essential tools, not optional refinements. What made this alliance extraordinary was that these abstract forms did not merely approximate nature. They matched experimental results with unmatched precision. Mathematics was no longer a descriptive language layered on top of reality. It became the primary guide to understanding it. Max Born belonged to a generation of physicists for whom mathematical discipline was not separate from physical insight. Trained rigorously in mathematics, he approached physical problems with a deep respect for formal structure. He believed that consistency and clarity in equations were not aesthetic preferences but indicators of truth. When quantum phenomena resisted classical visualization, Born did not try to force intuitive pictures onto them. Instead, he trusted the mathematics to reveal what could be meaningfully said about physical systems. This approach proved decisive in the development of quantum mechanics. The equations that described atomic behavior were often counterintuitive, but they were internally consistent and experimentally successful. Born recognized that the role of mathematics was not to provide comforting images, but to establish relationships between measurable quantities. Observables such as energy, momentum, and position were no longer represented as simple numbers, but as mathematical operators acting on abstract states. This shift was radical, yet it worked. The power of this mathematical framework lay in its ability to connect theory directly to experiment. Calculations based on quantum formalism yielded probabilities that matched observed frequencies with astonishing accuracy. Spectral lines appeared exactly where the equations predicted. Scattering experiments produced distributions that aligned precisely with mathematical results. Again and again, abstract calculations found confirmation in the laboratory. This convergence built confidence that the mathematics was not an artificial construction, but a faithful representation of physical reality. Born's contribution was crucial in clarifying how these mathematical objects should be interpreted. He understood that not every element of an equation corresponds to a physical object in the classical sense. The wave function, for example, is a mathematical entity defined in an abstract space, not a wave moving through ordinary space like water or sound. Its significance lies in how it generates probabilities for measurement outcomes. This distinction prevented confusion and allowed physicists to use the mathematics effectively without demanding unnecessary visual analogies. By emphasizing the operational meaning of mathematical expressions, Born helped establish a new standard for physical explanation. A theory was judged not by how easily it could be visualized, but by how clearly it connected calculations to observations. This shift freed physics from the limitations of everyday intuition. It allowed scientists to explore realms where classical images fail, guided by equations that remained precise and reliable. The success of this approach reshaped the culture of physics. Mathematical rigor became central, not optional. Physical insight was measured by the ability to work within abstract frameworks and extract testable predictions. This did not eliminate creativity, it redirected it. Creativity now involved discovering the right mathematical structures rather than inventing mechanical models. The universe, it seemed, was written in a language more subtle than human imagination had anticipated. This marriage of mathematics and reality also carried philosophical implications. It suggested that the deepest layers of nature are not directly accessible to the senses. What we observe are outcomes shaped by underlying structures that can only be grasped through formal reasoning. Mathematics became a bridge between human cognition and a reality that resists direct visualization. The legacy of this perspective is evident throughout modern science. Quantum field theory, particle physics, and emerging quantum technologies all rely on highly abstract mathematics. Yet their predictions remain among the most accurate ever achieved. This enduring success traces back to the moment when physicists like Max Born chose to trust mathematical consistency over classical intuition. In accepting that mathematics could lead understanding rather than follow it, quantum mechanics transformed the meaning of explanation. Physical reality was no longer something that had to be pictured in familiar terms. It was something that could be known through structure, relation, and probability. This shift did not distance science from reality. It brought it closer, revealing a universe whose deepest order is expressed not in images, but in equations. The development of quantum mechanics is often told as a story of brilliant individuals and revolutionary ideas, but its true strength came from an environment where knowledge was shared, challenged, and refined collectively. Max Born played a central role in creating such an environment. More than a contributor of theories, he was a cultivator of minds. Through his teaching, guidance, and intellectual generosity, he shaped a generation of physicists who would go on to define modern science. At the University of Göttingen, Born helped transform the institution into one of the world's most influential centers for theoretical physics. The atmosphere he fostered was rigorous yet open, demanding yet collaborative. Young physicists were encouraged to question assumptions, test ideas against mathematics, and engage in relentless discussion. Born did not impose dogma. Instead, he guided inquiry, helping students sharpen their reasoning while respecting the uncertainty inherent in emerging theories. Among those who benefited from this mentorship was Werner Heisenberg, whose work on matrix mechanics became a cornerstone of quantum theory. Born recognized the importance of Heisenberg's ideas early, providing mathematical clarity and legitimacy to work that initially appeared strange and inaccessible. By helping translate Heisenberg's physical intuition into a coherent mathematical framework, Born ensured that the theory could be understood, developed, and tested by others. Wolfgang Pauli, known for his uncompromising intellectual standards, also passed through Born's influence. Pauli's critical thinking and conceptual precision were nurtured in an environment that valued depth over convenience. Born's insistence on mathematical consistency and conceptual honesty left a lasting mark on Pauli's approach to physics. Even when Pauli challenged prevailing ideas, including those of his mentors, he did so within the rigorous standards that Born had helped instill. Born's mentorship extended beyond formal supervision. He created networks of collaboration that connected some of the brightest minds of the era. Göttingen became a crossroads where ideas from different approaches converged. Discussions were intense, often contentious, but always grounded in mutual respect for evidence and logic. Born understood that scientific progress thrives in communities where disagreement is not suppressed but structured. What distinguished Born as a mentor was his humility. Despite his own profound contributions, he did not seek to dominate the narrative of quantum mechanics. He willingly credited others, supported their breakthroughs, and stepped back when necessary. This attitude created space for innovation. Students felt free to pursue unconventional paths without fear of intellectual overshadowing. The political upheavals of the 1930s forced Born into exile, disrupting the physical center of this intellectual community. Yet his influence did not fade. From abroad, he continued to correspond, teach, and inspire. His ideas and standards traveled with his students, shaping research institutions across Europe and beyond. The culture he had helped establish proved resilient, surviving displacement and adversity. The legacy of Born's mentorship is visible in the structure of modern physics. Quantum mechanics did not develop as a collection of isolated insights, but as a coherent framework refined through dialogue and critique. Born's role in training physicists to think probabilistically, mathematically, and cautiously about interpretation ensured that the theory matured without collapsing under philosophical confusion. Beyond technical training, Born imparted a model of scientific integrity. He demonstrated that authority should never override evidence, and that elegance must be earned through consistency, not imposed through intuition. This ethos became part of the professional identity of theoretical physics. It shaped how research was conducted, how results were evaluated, and how knowledge was transmitted to future generations. The impact of this mentorship reaches far beyond the individuals directly involved. Many of Born's students trained others, extending his influence across decades. Entire branches of physics carry the imprint of his approach, valuing clarity, collaboration, and respect for uncertainty. The technologies and theories that emerged from quantum mechanics owe as much to this intellectual culture as to any single equation. In the end, Max Born's greatest contribution may not be a specific interpretation or formula, but the people he helped shape. By building minds capable of navigating uncertainty with discipline and imagination, he ensured that quantum mechanics would become not just a revolutionary theory, but a stable foundation for modern science. The emergence of probability as a fundamental principle in physics did not occur without resistance. For many of the greatest minds of the 20th century, the idea was not just scientifically troubling, but philosophically unacceptable. Physics had long been regarded as the discipline that revealed necessity in nature, uncovering laws that governed every event with certainty. To suggest that chance lay at the heart of reality seemed, to some, like an admission of defeat. Max Born found himself at the center of this controversy, defending an interpretation that challenged centuries of scientific tradition. The strongest opposition came from those who believed that randomness could only reflect incomplete knowledge. Albert Einstein famously expressed his discomfort, insisting that the universe could not be governed by chance. For him, probability was a temporary placeholder, a sign that quantum mechanics had not yet reached its final form. He was convinced that deeper, hidden variables must exist, restoring determinism beneath the surface of apparent randomness. Born understood Einstein's concern and shared his respect for logical clarity, but he did not share his conclusion. Born's response was measured and principled. He did not claim that probability was philosophically satisfying. Instead, he argued that it was empirically unavoidable. The equations of quantum mechanics, when interpreted probabilistically, produced results that matched experiments with extraordinary precision. Attempts to impose deterministic explanations consistently failed or required assumptions that conflicted with observed phenomena. Born believed that science must follow evidence even when it leads to uncomfortable conclusions. This controversy extended beyond personal disagreements. It reflected a deeper tension between different conceptions of scientific explanation. One side sought underlying mechanisms that guaranteed specific outcomes. The other accepted that laws might govern distributions rather than individual events. Born aligned with the latter view, not out of philosophical preference, but out of methodological discipline. He insisted that a theory should not claim more than it can justify through observation. As quantum mechanics matured, challenges to the probabilistic interpretation became increasingly sophisticated. Proposals involving hidden variables and non-local influences were explored in detail. Mathematical tests were developed to distinguish between deterministic and probabilistic theories. When experiments were eventually performed, their results consistently favored the quantum predictions. The universe behaved in ways that no deterministic model could fully explain without sacrificing other fundamental principles. Over time, resistance gave way to acceptance, though not without lingering discomfort. Even those who disliked the implications were forced to acknowledge the theory's success. Quantum mechanics proved capable of explaining atomic structure, chemical bonding, nuclear processes, and a vast range of phenomena with unmatched accuracy. Its probabilistic core was not a weakness to be eliminated, but a strength that enabled its predictive power. Born's position gained further credibility as technology advanced. Devices based on quantum principles operated reliably despite their reliance on probabilistic laws. The consistency of these technologies demonstrated that probability could form the basis of precise control and practical application. This undermined the argument that determinism was necessary for scientific reliability, yet Born never dismissed the philosophical unease surrounding his ideas. He recognized that accepting probability as fundamental required a shift in how humans understood causality and explanation. He viewed this shift not as a loss, but as an expansion of perspective. Nature, he suggested, might not conform to human expectations of certainty, and science must adapt accordingly. The eventual recognition of Born's contribution, including the awarding of the Nobel Prize, symbolized more than personal achievement. It marked a broader acknowledgement that the probabilistic interpretation had withstood both experimental scrutiny and philosophical challenge. What was once controversial became foundational. This episode in the history of science illustrates how progress often requires patience and resilience. Revolutionary ideas rarely gain immediate acceptance, especially when they challenge deeply held assumptions. Born's quiet persistence, grounded in evidence and clarity, proved more powerful than rhetorical persuasion. In the end, the controversy surrounding probability reshaped physics in a lasting way. It clarified the limits of explanation, redefined the meaning of law, and demonstrated that uncertainty can coexist with precision. By standing firm in the face of resistance, Max Born helped establish a framework that continues to guide our understanding of the quantum world. The influence of Max Born's ideas extends far beyond the early debates of quantum mechanics, reaching deeply into the structure of modern science and the technologies that shape everyday life. What began as a careful reinterpretation of mathematical symbols evolved into a framework that defines how humanity understands and interacts with the microscopic world. The acceptance of probability as a fundamental element of nature did not limit scientific ambition. It expanded it, opening pathways that deterministic thinking could never fully explore. Modern physics rests on the assumption that quantum laws govern matter and energy at the most basic level. From the behavior of electrons in atoms to the interactions of subatomic particles, the probabilistic framework introduced by Born underlies every accurate description. Quantum field theories, which describe the fundamental forces of nature, inherit this probabilistic structure. Predictions in these theories are not guesses. They are statistical outcomes calculated with extraordinary precision. Experiments confirm them to many decimal places, reinforcing the idea that probability is not a sign of weakness, but a mark of deep understanding. The technological consequences of this framework are profound. Semiconductors, the foundation of all modern electronics, operate because electrons occupy quantized energy states and move according to probabilistic rules. The reliable functioning of transistors depends on calculations rooted in Born's interpretation. Lasers, which produce coherent light used in communication, medicine, and industry, rely on quantum transitions governed by probability amplitudes. These devices do not work despite quantum uncertainty. They work because of it. Medical technologies also reflect this legacy. Imaging techniques and radiation therapies depend on precise knowledge of how particles interact with matter at the quantum level. The ability to predict statistical outcomes allows physicians to harness processes that would be impossible to control deterministically. The same probabilistic principles guide the design of sensors, detectors, and measurement tools used across scientific disciplines. In recent decades, the rise of quantum information science has brought Born's ideas into even sharper focus. Quantum computing, encryption, and communication all exploit the probabilistic nature of quantum states. These technologies do not attempt to eliminate uncertainty. They use it as a resource. Superposition, entanglement, and measurement outcomes are all governed by probability distributions. The reliability of these systems comes not from predicting single outcomes, but from controlling the structure of possibilities. Beyond technology, the conceptual impact of Born's work continues to shape scientific thinking. Probability has become an accepted part of explanation, not a temporary placeholder for ignorance. Scientists now routinely build theories that predict distributions rather than certainties, confident that such predictions can be both meaningful and precise. This perspective has influenced fields outside physics, including chemistry, biology, and even economics, where probabilistic models provide insight into complex systems. Philosophically, the legacy is equally significant. The probabilistic view challenges the notion that the universe unfolds according to a fixed script. Instead, it suggests a reality that is structured yet open, governed by laws that define possibilities rather than dictate outcomes. This view has inspired new approaches to understanding causality, time, and information. It has encouraged dialogue between science and philosophy, each refining the other's assumptions. Max Born's influence also persists through education and scientific culture. The standards he helped establish, mathematical rigor, interpretive humility, and respect for empirical evidence, remain central to theoretical research. Students are trained to accept abstraction as a necessary tool and to evaluate theories by their predictive success rather than their intuitive appeal. This intellectual discipline is one of the enduring strengths of modern science. Perhaps most importantly, Born's legacy demonstrates that scientific progress often requires redefining what counts as understanding. To know something is not always to predict its exact behavior, but to grasp the structure within which it behaves. Probability provides that structure at the quantum level. It tells us what can happen, what cannot, and how likely each possibility is. Within these boundaries, nature expresses its richness. The world shaped by quantum mechanics is not one of chaos, but of subtle order. The laws are precise, even when outcomes are not. This balance between certainty and uncertainty has proven to be one of the most productive ideas in the history of science. Through his insight and persistence, Max Born helped reveal this balance, leaving a legacy that continues to guide both thought and technology in the modern age.